n plus 1 factorial times x minus 2 to the n plus 1 divided by n factorial times x minus 2 to the n. And of course we can simplify n plus 1 factorial divided by n factorial is just n plus 1. And then x minus 2 to the n plus 1 over x minus 2 to the n is just x minus 2. Okay? And if you put the absolute value, we have the absolute value. And then when you take n to infinity, x should be any number. When n go to infinity, the whole thing go to infinity. As n go to infinity. Of course, if the limit is infinity, the ratio test say what? The series is divergent. Okay? Except for 2. So for this problem right here, the radius conversion is r equal to 0, and interval conversion now just 1 point at 2. Interval conversion is just 1 point. Radius is 0 because we assign the point 2 right here. The series will not be convergent at any other point. Okay? Because the limit right here is infinity. Okay, it's not a finite number. Now, show you another example that you actually have a power series conversion everywhere. It means that r equal to infinity is conversion for any value of x. And this is a very famous series talking about the function e to the x. So what? Well, x to the n over n factorial. The previous one I multiply, now I divide. N equal to 0 to infinity. So this is what? 1 plus x squared, or plus x I mean. X plus x squared over 2 factorial, x cubed over 3 factorial, x squared over 4 factorial plus data. Okay? And this one center is at a equal to 0, right? This is the center at 0. Center at 0. Okay? So x minus 0, alright? We want to test for the conversion. We use a ratio test again. So the general term an is xn over n factorial. An plus 1 is x to the n plus 1 over n plus 1 factorial. We're going to do an plus 1 over an, make a ratio. So this divided by this means multiplied by its reciprocal. So let me make it quick. X to the n plus 1 over n plus 1 factorial. Divide by this number means multiply by its reciprocal. So n factorial over x to the n. And simplify. X to the n cancel out. You have the x left. N factorial over n plus 1 factorial. So 1 over n plus 1. And then times x. Okay. So absolute value. You got the absolute value in here. And n go to infinity, that thing gonna go to 0. Doesn't matter what value of x is. Okay, x is a specific number, any number. Okay, fixed. N go to infinity, and this thing gonna go to 0 as n go to infinity. Okay, so the limit is equal to 0, always less than 1. So that series will always be convergent. Okay, so the radius conversion r is equal to infinity. So the interval conversion will be from negative infinity to plus infinity, center at 0. So 0 minus infinity, 0 plus infinity. Okay. So we have a couple of examples to see that power series is going to be conversion for sure at the center, and then it could be conversion a little bit more to the left, more to the right. Our job in this section is to find the radius conversion. Okay, how far it is from the center, still convergent. And after having the radius, you can find the interval conversion. The only difference is after you have the radius, you'll be able to find the interval, except for the endpoint. And how to take care of the endpoint? Just plug in the endpoint into the series. You should have the answer. Okay. Let me give you another example. This one is an easy one. So you see more about the example of radius finite number. Okay. How about this? The sum of x plus 3 to the n run from 0 to infinity. And this is what? 1 plus x plus 3 plus x plus 3 squared plus x plus 3 cubed plus actually this is geometric series, okay? You know it's conversion at the center, -3, and then radius is 1 already. But let me show you all the steps. See it. But this is Cn's all equal to 1 all the time. Okay? The coefficients all 1. Okay. We actually don't even need to write that. But and then what? The general term an is the whole thing, x plus 3 to the n. An plus 1 is going to be x plus 3 to the n plus 1. All right? So ratio test, take an plus 1 over an will be x plus 3 to the n plus 1 over x plus 3 to the n, which is x plus 3. Okay? Take the absolute value. You got the absolute value. Okay? Now we have to take care of this limit. This limit right here is not a constant. It depends on x. 3 cases. The first one, x plus 3 less than 1. And that means -1 less than x plus 3 less than 1. And that means you subtract the 3 on the other side. You got -4 less than x less than -2. It is absolute convergence by the ratio test. In the second case, if x plus 3 equal to 1, and we don't know yet, inconclusive, right? And then x plus 3 is bigger than 1, this is divergent. And actually, I claim that you don't have to do them all because this is less than 1, you have this, right? Then bigger than 1, I mean. Then what? X is going to be less than -4 or bigger than -2 with the, on the complement of this one. And 1 right here means what? At the endpoint right here means what? X equal to -4 or x equal to -2. We have to test what? See? Equal. And -4, -2. We have to test for the point. Need to test. Need to check. Okay. So graphically, -3 is right here. The interval from -4 to -2. So obviously, you see the radius is 1. Okay. Center that's -3. Let's go 1 to the left, go 1 to the right. Okay. We have to test for the endpoints. X equal to -4 and x equal to -2. See what happens. Let's text x equal to -4 first. -4, you plug in here, you have what? The sum is x plus 3 to the n. 1, -4, so -1. Then what? Plus 1, -1, plus 1, -1, plus the other. And this is divergent. Alternating series. 1, 1, 1 all the time, so the sum is undefined. For the other one, x equal to -2, you got what? Sum of x plus 3 to the n is equal to 1 plus 1 plus 1 plus 1 plus 1 is still divergent. 2 different types of divergent. This divergent, the sum is undefined. This one right here, the sum is infinity. So both divergent. So we don't have any convergence at the endpoint. So we have the radius conversion is 1. The interval conversion is from -4 to -2. Okay? Parenthesis, both sides, because we don't have any convergence at the endpoints. Okay. So this is actually the end of 11.8. Let me double check to see if I missed any item in this section before I move on. Yes, not. So let me move on to 11.9. I will be talking about presentation of a function as a power series. Presentation of functions as power series. Okay. So the idea in this section is this. Is there any way we can represent a function as a power series? Okay, so in this section we only learn some special type of function, and later on in the next section we learn that more general type of function we call analytic function. If a function is differentiable all the time, then yes, it'll be able to be written as a power series. So let's start with something that we know. The sum of x to the n running from 0 to infinity. This is 1 plus x squared plus x cubed plus this is what? Geometric series, right? Okay? And then if the center is at 0 and the interval conversion is -1 to 1. Okay, so conversion to when -1 is less than x, less than 1 will be convergent. Okay? And when x is between -1 and 1, that series will be equal to then 1 plus x squared plus x cubed will be equal to 1 over x, 1 minus x. Okay? That's what we learned before. When x is between -1 and 1, center at 0, radius 1, so -1 to 1, not including the endpoints, then what? This series will be convergent. Okay? So, think of it a little bit backward. If I have a function f of x equal to 1 over 1 minus x, I have a function. This is a rational function. You all know, okay? And we have some condition for the domain x. Is the domain is between -1 to 1. -1 less than x. -1 is less than x, less than 1. This is the Romano function, not all real number anymore. It's just all the value of x between -1 and 1, not including the endpoint. Then I claim that this function 1 over 1 minus x can be represented as the power series right here. Okay, so that's all I'm saying. So f of x equal to 1 over 1 minus x, with x between -1 and 1, and f of x, instead of writing 1 over 1 minus x, you can write it as 1 plus x squared plus x cubed plus forever. Okay, and this is the main point for this section. We can represent a function as a power series. Okay, using the geometry series that we learned right here. Okay. Now, what do we get from here? I need some room to write. Let me try to write small down here. What if I have the function this? Say, a different function. Say g of x is equal to 1 over x plus 1 plus x. How can I represent this as a power series? I can think of it as what? 1 over 1 minus negative x. Okay? Plus x is 1 minus negative x. So this is no more than a function f of negative x that you have right here. So g of x is actually f of negative x. Is that right? Because you replace x by negative x, you have 1 over 1 minus negative x, which is what you have right here. And this function, 1 over 1 plus x, can also be represented as a power series. What? 1 minus x, right? Plus negative x squared plus negative x cubed plus negative x to the 4 plus If you simplify, 1 minus x plus x squared minus x cubed plus x to the 4 minus so it's alternating. Okay? And for this one is x between -1 and 1. For this one right here, negative x gonna be in between -1 and 1. And actually you have the same. Multiply both sides by -1. You have 1 is greater than x, less greater than -1. And the same interval conversion. Okay? Try one more example, a couple more actually. What if I have the function g of x is equal to 1 over 1 plus x squared? I know this already. How can I use the function f of x to find the power series for the function g of x right here? Same strategy. If I have this, and now I'm going to modify this a little. Say what? 1 over 1 minus negative x squared. Pretty much same idea, right? So this is no more than f of negative x squared. Okay, f of x is 1 minus x, 1 over 1 minus x, so what? F of negative x squared is 1 over 1 minus negative x squared. This is, we plug in here for function 1 plus negative x squared plus negative x squared plus negative x squared cubed plus negative x squared to the 4 plus dot dot dot. And simplify, you got 1 minus x squared plus x to the 4 minus x to the 6. See, 2 times 3 is 6. And plus x to the 8, even power cancel out the negative sign. And plus or minus dot dot. Okay, we can actually represent another function as a power series from the original one that we know. Let me try to find harder examples, so make sure that you guys can have it in general. So let me look at the exercise, see if we have any harder one. Okay, I see one. G of x equal to 2 over 3 minus x squared, for example. Okay, so it's kind of looks like this. It's not quite, not really, but we try to modify it so we make it look like 1 over 1 minus a variable, and of course we can have a constant outside. Okay, so if I factor the 2 out, I got 1 over 3 minus x squared. We're getting closer to what we have, so I factor the 2 out, right? 2 times 1 is 2. And then same thing if I factor the 3 out on the bottom, so really 2, then 1 over, right? I don't really need the parentheses if that's any clearer to you. Okay? Then if I factor the 3 out on the bottom, what do I have? 1 minus x squared over 3. In other words, this is 2 over 3 times 1 over 1 minus x squared over 3. Alright, I factor out the 2 from the top, so I got 2 times 1, which is 2. The bottom, I got the 3 right here, and I want to have a 1, so I just divide everything by 3. So factor out the 3, that's what I'm saying. So 3 out, you got 1 times 3 is 3, right? 3 times x cubed over 3 is x squared over 3, which is x squared. So what is so good about this? And this is no more than 2 over 3 times f of x squared over 3. Alright, so f of x is this. F of x squared over 3 is 1 over 1 minus x squared over 3. And you're going to use time a constant in front. Okay? So you distribute, and then the rest is going to come out. I guess I don't need to write more, because f of x squared over 3, you guys know this already. And then just time a constant. You have the power series. Okay, you may have this, you may see this. Say g of x is equal to x cubed over 1 minus x. Same idea, now in the numerator you got variable x, so you got to think of it this way. X cubed times 1 over 1 minus x. And this is no more than x cubed times f of x. Okay, this is 1 over 1 minus x, f of x right here. So this is what? X cubed times 1 plus x squared plus x cubed plus da da da. You just distribute, you got what? X cubed plus x to the 4, x to the 5th plus da da da. You're done. Okay? So from the original power series right here, which is the geometric series with radius convergence r equal to 1, center at 0, you can find the power series for many more functions. Okay, more than that, we have a theorem. Let me see if they put the theorem in this section or in the next one. Oh, right here. Okay, so let me write in general. The theorem says this. If you have a power series Cn x minus a to the n, okay, n root from 0 to infinity, this series was C0 plus C1 x minus a. I just try to write down the whole thing so you guys can see it better. C2 x minus a squared, C3 x minus a cubed plus dot. And if this series is convergent on the interval, the radius r, so it could be what? A right here, all the way to what? A minus r to a plus r. I try not to write interval conversion because I don't know about the endpoint yet. Could be square bracket like this, a minus r to a plus r, or could be parenthesis. I don't know. So I'll write this way with the radius of convergence r, center at a. Okay, so this power series convergent when x equal to a, and then radius convergent r. Then the theorem says this: you can actually differentiate, means to take derivative or integrate. So if you call this is f of x, then f prime of x will be what? You can take the derivative of this. Constant derivative 0. This one, you take the derivative, you got what? C1 plus 2C2 x minus a 3C3 x minus a squared plus dot dot dot. Okay. So you have a convergent power series. You take the derivative of that power series. You still have a convergent series. You center at a, and center at a radius convergence r. Okay, same thing. And then not just taking the derivative, you can do what? Integral. So integral of f of x. You can actually integrate the power series right here. You got what? C0x. Oh, I need to have a constant in front, right? Constant c plus what? C0x plus what? 1/2 C1 x minus a squared, because I integrate this, right? A constant antiderivative is going to be constant times x. It's x minus a. Antiderivative is going to be this, plus 1/3 C2 x minus a cubed plus 1/4 C3 x minus a to the 4th plus dot dot. And this series is also convergent with radius r. Same r, same center, same radius convergent. Okay. Pretty much the theorem says you have a power series center at a, radius convergent r, then you can take the derivative. You can integrate the function of the power series, and you still have the same properties, center and radius convergent. Okay, what is it good for? We have more function can be represented as a power series from this. Example. What is ln of x minus 1? How about x plus 1? Doesn't matter. X plus 1 as a power series. Okay, this is my f of x. I want to find the power series of ln of x plus 1. And I don't know it directly, but I see that I can take the derivative, see what I got. So f prime of x will be 1 over x plus 1. Let me write it as 1 plus x and make it look like x plus 1 or 1 plus x is the same thing. Okay, it looks like the function that we have. Derivative of f of x is derivative of ln is 1 over whatever inside ln, so 1 plus x, and then times the derivative of x plus 1, which is 1. I'm using the chain rule. I have this. Okay, and you find the power series of this already. This is what? 1 minus x plus x squared minus x cubed plus x to the 4 minus x to the 5th plus dot dot, which I did it a minute ago. So if you know this, can you find the antiderivative of this, which is going back to ln? Be careful because you may have a constant, right? So the integral of f prime of x dx, which is the integral of 1 over 1 plus x dx. Okay. And antiderivative of this is what? Which is ln of 1 plus x and then plus c. See? Ln integral of 1 over 1 plus x is ln of 1 plus x, and then don't forget the constant plus c. And now you can integrate that power series right here and see what you got. Integral of 1 is just x, minus x become minus 1/2 of x squared. X squared become plus 1/3 of x cubed. Minus x cubed become minus